Okay. Morning, everybody. Morning, Jake. Always good to see you. All right, let's begin. The attendance poll, 787. The class is awfully thin today. I hope there are people on Zoom. And my TAs should be here any minute. We're going to continue with our sequence of lectures on recurrent neural networks, but we are specifically going to switch to a problem of using these to convert one sequence to another. Now, as we'd explained, recurrent neural networks are all about analyzing time series, sequences of data. And you'd analyze a time series, a sequence, and produce an output, which could be either a single output or a sequence. The generic setting is to think of it as a sequence-to-sequence converter, where some sequence x1 through xn goes in, some other sequence y1 through ym comes out, and there need not be any correspondence between n and m. So the length of the sequence that goes in need not bear any direct relationship to the length of the sequence that comes out. So examples like speech recognition. Speech goes in, a word sequence comes out. Machine translation. One word sequence goes in, another word sequence comes out. Or dialogue systems. You say something, the system responds with something else, and there's no direct correspondence between your query and the response. The query could be long and the response could be short, or vice versa, right? Question answering, and so on. So there's no assumption of any kind of synchrony. We can broadly categorize sequence-to-sequence conversion problems to two. One in which there is some kind of an order correspondence between the input and the output. That's for speech recognition, for instance. Or the other in which we cannot even make an assumption of such a correspondence. For example, in machine translation or dialogue systems. In MT, if I were translating I ate an apple to Ishaba and an Apfel gegessen, and then the order of the words that went in is very different from the order of words that came out. There is not even a one-to-one correspondence between what went in and what came out. So we've been looking at, a dialogue system. You say, my screen is blank, and the system responds with, please check if your computer is plugged in. There's no correspondence, right? So the specific problem we've been looking at is this one. We'll continue with this for this week. And next week, we will talk about the latter kind of problem. So here's what we had. You had an output that was order aligned with the input, but not time synchronous. So which means that the initial portion of the output corresponds to the initial portion of the input. The latter portion of the output corresponds to the latter portion of the input. If you reorder the input, the output is likely to change in a very predictable manner. But this also means that in general, the number of output symbols is going to be lesser than or equal to the number of input symbols. So the problems we saw were how do we perform inference on such a model, how to output time asynchronous sequences, and how do we train such models. And for performing inference, we sort of partially addressed this. We will return to this problem later in this lecture. We were looking at how to train such models. And we saw that typically you'd be given input and output sequences. Now, if the output sequence, if you were given the alignment for the output sequence, then you would know exactly where each output symbol was produced. And so you could just compute the divergences at those points, or you could make the output time synchronous by repeating each symbol through the portion of the input to which it corresponded. And now this became a time synchronous problem. And we also saw that in this case, the divergence simply becomes the negative of the sum over all time instance of the log likelihood assigned to the target output symbol at that time. So it just became minus of summation t log of the probability assigned to the specific target symbol at time t. Now, this thing is important. Please keep track of it. We're going to see it a few times. And so here again is the divergence. It's the negative of the summation over all time of the log of the probability assigned to the target symbol at each time. If I were to take the derivative of this divergence with respect to the output of the network at any time, then that's simply going to be zeros for all the symbols that are not the target symbol. And for the target symbol alone, the derivative is going to be -1 over the probability assigned to the symbol. And you can see again, this is just your standard derivative of the KL divergence. We've seen this back in lecture 3. So the bigger problem is, well, how do we train when the alignment is not provided? So I've given you the output sequence, but I've not told you where in time each symbol occurs. In this case, we saw one way of solving the problem. I could give you some initial alignments. I can train some models with it. Then I can use those models to obtain new alignments and cycle through. And eventually, we can find out, once you obtain new alignments, you can actually use gradient descent to update the models. And the updated models could go back and be reused to re-estimate the alignments. The re-estimated alignments could be used to update the model again, and we could keep iterating, and eventually it would converge. That would be our final model. And so here's our first poll. And of course, we did the alignment using the Viterbi algorithm. We saw this too. Okay, guys. What's the answer to the first question? Anybody? Say something, Rishabh? True. What about the second one? True. So Viterbi training explicitly estimates the alignment of each training instance and computes the divergence for the estimated alignment. And so it requires re-estimation of the alignments in each iteration. And we saw that this can be problematic. And this is problematic because it's heavily dependent on the initial alignment that you provide. If the initial alignment you provide is crappy, then it's going to give you poor local optima, which means that the models that you learn are not going to be very good. So lady over there, can you shut your laptop, please? Thank you. So guys, this is the last time I'm going to tell one of you to shut your laptop. The next time I find someone with a laptop open that should not be open, I'm going to ask you to leave the room, just to let you know, okay? So the second approach that we considered was not commit to any particular alignment, but to actually consider all possible alignments. So what do we mean by this? Now remember that when I wanted to align my input to the symbol sequence that I was given for the input, the first thing I did was to run the input through the network. The network gave me a probability table, the probability for every symbol at every time. So from this probability table, I pulled out the rows corresponding to the symbols in the output, and I constructed a second table which consisted only of the probabilities assigned to the target symbols in the order in which they occur. So here, for example, the symbol sequence, the output is beefy. So my table has the row for B, the row for E, the row for fur, and then the row for E again. And when we constructed a table of this kind, then we found that any path from the top left corner to the bottom right corner naturally gave you an alignment of the input to the symbol sequence. And in fact, when we were trying to estimate the alignment, what we were doing was trying to find the most likely path through this graph, where the graph represents all possible ways of going from the top left to the bottom right that constitute a valid alignment. So now, instead of finding the most likely path, here's a different view to this. Once I have a graph of this kind, this is, let me just draw a sample graph, just a tiny one. And so let's say just 3 symbols and 4 time instants. Then your graph is going to look something like this, right? This is the only portion of the graph we really need to be worried about. Nothing else is going to go here. Now, on this path, on this graph, there are many different ways of going from the beginning to the end. Each one has its own probability. So if I normalize, so there are 2 things you must consider. If I have a symbol sequence S1, S2, S3, then what do you think the total, so now there's an input X1, X2, X3, X4, right? If I added up the probabilities of all the paths from the beginning to the end, what would that be? What probability is that computing? Anyone? So if I just added up, so if I thought of every possible way, the total probabilities of all paths through this graph is the total probability of every possible way of aligning S1, S2, S3 to X1 through X4. So that is simply going to give me P of S1, S2, S3 given X1 through X4. Because you're considering every possible way of aligning the input to the symbol sequence. Now, given this, now every individual path, let me just call them P1, P2, P3 for convenience, right? So each path through this graph has its own probability. So if I think of this, these paths over themselves have a probability distribution, every possible alignment. And so when I pick the most likely path, all I am doing is picking the one path that has the highest probability. But the other way to think about it is to say I'm actually going to consider the average over all paths. So what would this mean? Here's one path. If I use this path, that path is going to have some loss, some divergence. So I can take path 1 times the probability of path 1. Then here's another path, right? So this is path 2, the loss of path 2, right? Times the probability of path 2, and so on. So if I take the expected divergence over all possible paths, which is the same as summing over all paths, the loss corresponding to that path, corresponding to the alignment represented by that path, multiplied by the probability of the path itself. That is averaging over all paths, all alignments. And more specifically, it's assigning greater importance to alignments which are more likely and less importance to alignments which are less likely. So this is a lot more non-committal way of computing a loss that you can minimize, and it's less likely to run into local optima. But then, what exactly is the loss of any path? The loss for any path, as we saw, is the sum over all of the nodes in the path, so sum over all time of the log likelihood of the symbol, target symbol, at that time in that alignment, right? And now, this is an expectation of a sum. So is this making sense to you guys, right? Yes, no? Okay, yeah.
What did you use mean again?
The mean? So you have many different alignments. Corresponding to each alignment is a loss. So the average of these losses is the expected loss. Okay. The loss multiplied by the probability of the alignment itself, okay? Yes?
when you calculate the mean, you won't get to know what the actual path is, right? How will you know how many IFIs or how many Fs are coming into your sequence?
We're averaging over all possible alignments. So you're not actually considering any particular sequence, are you?
So, but you need to output the correct value, right? How do you do that?
So this, okay, how would you compute this? So hang on, bear with me, right? So here's the thing. I'm going to take advantage of something. It's the expectation of a sum. What do we know about expectations of sums? They are sums of expectations. So I can move the expectation into the summation. But hang on, here's a poll. All right, Jake's my clock. It's done. So someone on Zoom, can you answer the first question? Is there anybody on Zoom's? Is it
True.
true?
Sure.
Okay. Does everybody agree that the first question? What about the second one, guys? False? Okay. Because when you're training without alignment, you're computing the average divergence over all possible alignments, which means you don't have to determine any specific alignment. They're all being considered, right? And now going back here, I have an expectation of a sum, which means I can make that the sum of an expectation. Now, but what is an expectation? An expectation is, so this means the divergence is the negative of the sum over all time of the average divergence at that time. So going back over here to this graph, what I would be summing over all time. At each time, I have several nodes in my graph. And what does this node represent? This node represents the event that in aligning this input sequence to this input, symbol S1 was aligned to X2. That's what each node represents, right? And so this node itself has a log probability. We're computing the average log, again, this is the average log probability at each time. You're summing across all time, and then at each time, you're taking the average log probability of the nodes at that time, right? So this node has a log probability, which was the probability assigned to symbol S1 at time 2 by the network, the log of that. Each of these nodes would have a corresponding term, right? So if I want to compute the average negative log probability over here, I'm going to multiply the negative log probability of this node by the posterior probability that the alignment of the input to the symbol sequence aligns S1 to X2, right? Times the log probability at this node times multiplied by the probability that the alignment aligns S2 to X2 plus, again, this guy, right? The log probability of this node multiplied by the probability that the alignment aligns S3 to X2. That makes sense, right? So this term here is the probability of aligning a specific symbol, which in this case is ST, to a corresponding input. So you eventually want to multiply, so you are summing across all time. So what this loss really became was this. You're summing across all time, and at each time, you're summing down the column, and the term that you're summing is the log probability at this node multiplied by the posterior probability that when you align this guy to this one, that alignment goes through this node.
the sentence?
Okay, so again, we are summing across all time. That's what we did, right? But at each time, you want the expected loss or the expected negative log probability at that time, which is simply going to be the sum over all of the nodes of the negative log probability assigned with the node multiplied by the probability that when you align this input to the symbol sequence, that alignment aligns S1 to X2, for instance.
Posterior. Why is it posterior? What's getting the terminology? Why is it called posterior?
I'm calling it posterior because it's conditioned on having this one and having this input sequence. So you're told that you're aligning this symbol sequence to this input. So if I tell you that I'm aligning S1, S2, S3 to the symbol sequence X1 through X4. So if I'm aligning, for example, bit to X1 through X4, and I've given you the audio, and I've told you that this is bit, then what is the probability that the B actually align to 2? That's the posterior probability of B aligning to 2 given bit and the input, right? So that's basically what this symbol sequence is. So the key problem here is this. How do you compute these posterior probabilities? Now again, what we really want to do is compute the probability that this symbol aligned to this input, given that this was the complete sequence and this is the complete input. Does that make sense to you guys? Right? That in turn, just Bayes' rule, is proportional to the probability of all paths that go through this node. So here, and that is the probability that we really want to compute. So go back and in my example, I have the node E aligning to the symbol 3. What is the posterior probability that when I align B phi to my input, that alignment is going to align E to X3? That is proportional to the portion of the graph that goes through the E3 node, because that represents all paths that align E to the third input. Does that make sense to you guys? So this blue highlighted portion of the graph over here, that represents all paths that go through this node, right? So the total probability of that graph is the total probability of all alignments that align E to the symbol, to the input 3.
Okay.
Was it clear? Okay. So this is what I really need to compute. There's no other path that aligns E to 3. So how do I compute this guy? How do I compute the total probability of this portion of the graph? Now, to compute the total probability of this portion of the graph, I'm going to decompose this into two parts. The portion of the graph that comes into the node and the portion of the graph that goes out of the node, okay? So the total probability of the pink portion of the graph highlighted in pink is the total probability of the portion of the graph encircled in blue times the probability of the graph encircled in red conditioned on the portion of the graph encircled in blue. So what does this mean? It is the probability of the total probability of all paths that align E to the third input is going to be the total probability of all paths that the total probability of all alignments of the first 4 inputs to the first 2 symbols times the total probability of the subsequent 5 inputs to symbols 2, 3, and 4, conditioned on that the initial portion aligned with E going to 3. That makes sense? Right, so I can just say, if I wanted something over here, this guy, just for convenience, let me extend this, something of this kind. So if I want the probability of this graph, that is the total probability of all paths that align this input to this symbol to this input. The way I can do it is to align this portion of the input sequence to this portion of the input and align the remaining input to this portion of the symbol sequence, right? And there's the conditioning. So the second portion, the total probability of this red graph, is conditioned on the third guy aligning to E, because that's what the rest of the graph is coming out of, right? So the total probability of the highlighted portion of the graph is the probability of aligning x0 to x3 to B, and the probability of aligning x4 to x8 to E given that x0 to x3 was aligned to B. That's the only way you can construct the complete alignment. Yeah.
E for EFE.
EFE. So I want this represents aligning EFE to x4 to x8. But that's conditioned on ending up over here, right? That's aligning B to x0 to x3. Okay. Now, that's all very fine. Now, something interesting happens. The conditioning goes away. And why is that? Now, the way we compute probabilities in your recurrent neural network, all the information is moved forward through the hidden layer. So, whether, if I were to be producing outputs, drawing outputs from this probability distribution here, which symbol I chose at time 1 has no influence on the probabilities I compute at time 2. Why is that? Because the probability table over here is derived entirely from the inputs. So x0 is used to compute this guy. x0 to x1 is used to compute this guy. The symbol that occurred over here has no bearing on the probability that you're computing at time 2. Make sense? Right. So again, does the fact, when I give you these inputs and I compute these probabilities, does the fact that the actual symbol here is B have any bearing on the probabilities that you compute at this time? Is the network considering B over here, right? It's not. So what this means is that there's no conditioning on the output. It's only conditioned on the input. So what this really means is that I don't need to actually figure out, I don't have to worry about the fact that the symbol at time 3 was E. The total probability of the blue portion of the graph doesn't really depend on how you compute the probability of the initial portion of the graph. So this sort of decomposes this problem into the product of two terms, the product of the orange or the pink portion of the graph, probability of the pink portion of the graph, and the probability of the blue portion of the graph. Making sense to you guys? And so I'm seeing a confusion. Did that make sense? All right. Okay. So I'm going to call this first term, the one that's underlined in red, the forward probability, because I'm going to compute it left to right. And the second term, which is in blue, the backward probability, because I'm going to compute it right to left. So this guy, it's typically represented as alpha TR. Alpha TR represents the total probability of all paths that align the rth symbol to the input at time t. In this case, t is 3 and r is 2, right? So how do you compute this alpha TR?
R is 1, right? R is 1, right?
Depending on whether you're indexing it at 0 or 1, right? That's okay. Yeah, r would be 1 in this case, you're right. But basically the point is this. Alpha TR is the total probability of this graph, which is the total probability of all paths that end up aligning E to 3. Okay. Now, how do you compute this? How can you end up at the symbol E at time t? There are only two ways in which you can do it. You can either align B to 2 and then transition to aligning E to 3, or you can align E, the green box, to 2, and then end up transitioning from E to 3. So the total probability of all paths that end up at this node is going to be the sum of the product of the total probability of all paths that go here and transition to this one, plus the total probability of all paths that end up here and transition to this one here. What is the total probability of all paths that end up here? Anybody? Using the same notation. Yeah. Yeah, so what would that be in our notation? Again, if alpha TR is the total probability of paths that end up at 3E, what is the total probability of all paths that end up at 2B? What would that be?
Alpha T minus 1.
You're saying?
Alpha T minus 1 R minus 1.
So this is simply going to be alpha 2B, right?
Yeah.
The total probability of all paths that end up here. What is this guy? Alpha 2E. And so I can just replace this by alpha 2B times Y3E, that's this one, plus alpha 2E times Y3E. This makes sense, the way I did it? So in other words, if I want to compute the total probability of all paths that end up at symbol R at time t, I have to sum over all the parents of this node. And all I'm doing is summing the alphas of all the parents of the node, and then multiplying it by the node probability. This makes sense to you guys? Right, very simple. And so once I have this, here's the overall probability. Alpha TR for any node is the sum over all parents of the node of the alphas for the parent times the node probability. This gives you a nice recursive algorithm. I can start off with so in our graph, any node has only two parents, which is alpha TR has a parent at t minus 1 R. It also has a parent at t minus 1 R minus 1. I sum the two alphas and multiply this by YTR. Let's see how this goes. Here's my graph. The grayed out portions of the graph are the portions that have no probability, right? At the 0th time, you know that the blacked out nodes have no probability because you cannot begin at those nodes in our alignment. So alpha T0 is simply going to be the probability of the node itself. That's the entire graph. If I start from the left corner, then I can so once I've computed the alphas for the first column, I can take a step forward and I can compute my alphas for all the terms in the second column. And all I'm going to do is go down this column, and for every node, I sum up the alphas of the parent. And then in this case, the parents are simply t minus 1 L and t minus 1 L minus 1, and then multiplied by the node probability. Once I've done this for this column, I can take a step forward, compute the same thing for the next column, and keep going forward till I compute alphas for every node in my graph. Does this make sense to everybody? So what this has so this means I have managed to compute this alpha TR term for pretty much every node in the graph in one forward sweep. And so once I do this, by the way, here's the other thing. If I look at the alpha at this bottom right node, that's the total probability of all paths that align my symbol sequence to my input. So that's simply going to be the probability of the symbol sequence itself. Yeah.
What's going to be alpha 0 because it has no parent, right? At t equal to 0.
Meaning?
Alpha 0.
So
T equal to 0, it has no parent.
So for the first column alone, it's just going to be the node probability. The sum of all the node parents is just 1, effectively, right? So now if I want to compute the probability of the pink portion of the graph, I would have performed my forward pass, and then I'm just going to read the alpha TR of the output of the forward pass. And so that I can replace this guy here with alpha TR that I computed going forward. So the thing that I'm left with now is the blue portion of the graph. How do I compute this? This is the total probability of all nodes leading out of all paths leading out of TR going to the end. But then, just to make things a little more convenient, I'm also going to, so this is the total probability of all of these paths, not including the orange node, right? Now, just for convenience, I'm also going to include the orange node. And so I'm going to actually consider the total probability of all paths starting from the orange node till here. So I'm going to call this beta hat TR. Beta hat TR includes the orange node. But what I really want is the portion of the graph that doesn't include the orange node, which I'm calling beta TR. but the relationship between the two is easy, right? So, which is beta TR is simply beta hat TR, from which I divide out the probability of the orange node itself. So this is straightforward. So now let's see how I can compute beta hat. This making sense to you guys? Right, so now, what are all the paths that go from Y3E to the bottom? There are only two ways in which I can go from Y3E to the bottom. I can go from Y3E to Y4E and then be in this portion of the graph. Or I can go from Y3E to Y4F and be in this portion of the graph, right? So the total probability of all paths that go from Y3E to the bottom right of the graph is going to be Y3E times the probability of this subgraph plus Y3E times the probability of this subgraph. That's beta TR. That's what I'm calling beta hat TR, right? So, and what is the probability of this portion of the subgraph? Again, anybody?
Depends on the parent.
Depends on?
Parent, which is the orange.
No, but I'm just asking, what is the total probability of all paths that go from Y4E till here?
Beta 4E.
That's just going to be beta hat 4E, right? And what is the total probability of all paths that go from here to the end?
Beta 4F.
Beta hat 4F. And so that's basically what we have. So I can just say it's Y3E times beta hat 4E plus Y3E times beta hat 4F. In other words, the beta hat at any node is simply the node probability itself times the sum over all the successors of the node of the beta hat for the successor nodes. Again, this is very straightforward. Right, so once you know this, you know how to compute betas for every node in the graph. I can start off at the bottom right. I know that I'm not allowed to end up at those blacked out nodes, so I can black them out. The beta hat for the bottom right node is simply the node probability itself. Then I can keep stepping backwards. At each time, to compute the beta hats, I just sum the betas. Once I've computed from here, I can take a step back. I can go up the column. And for every node, I can sum the beta hats for all of the children and then multiply the sum by the node probability. Once I've done this for this column, I can take a step back, compute it for this guy, take another step back, do it for this guy, walk my way all the way to the beginning of the graph. And now again, what this has given me is beta hat, which included the initial node. So I want to get back to beta from it, so I just divide it by the node probability itself, that's all. Okay, and so I have managed to, so here's the entire algorithm, right? I start off by just setting the beta hats for the final node, then I keep working my way back. At each time I go up the column, and I compute the beta hat for all the nodes in the column by simply summing the beta hats for all the children, and then multiplying by the node probability. And the beta itself is obtained by just dividing the beta hat by the node probability. And so at this point, when I go back to my graph, if I've done a backward sweep, I know the beta terms for every node in the graph, which means that the total probability for the highlighted portion of the graph that goes through a node TR. So Rishabh, do you want to go out and wash your face or something? So if I want to compute the total probability of all paths that go through a node TR, that's simply the product of alpha TR and beta TR. Easily done, once I've done the forward and backward passes. And so this alpha is computed by using what's called the forward algorithm. The beta is computed using what's called the backward algorithm. So this product of alpha and beta is going to give me the total probability of all paths that go through this node. But then if I want the conditional, so I'm going to get one of these for every one of the nodes in any column. But then if I want the conditional probability, given this, the input, given the symbol sequence and the input, what is the probability of aligning S3 to say X4? You want it to be computed so that, when you align the input to the symbol sequence, you're either going to go through this node or through this node or through this node. So the sums of their probabilities must be 1. So what we will do is normalize. You go down the column, you multiply alpha and beta, and you normalize this product term so that when you go down the column, the sum is 1. And this is what we call our gammas over here. These are, again, symbols. Gamma TR is the posterior probability of aligning the tth input to the rth symbol. This makes sense so far to you guys, right? And so here is my entire divergence. It's very straightforward. I would actually perform a forward pass going forward, compute the alphas for every node in the graph. I do a backward pass going backward, compute the betas for every node in the graph. Then at every column, at every node, the product of the alpha and beta normalized so that these terms sum to 1 down the column, give me my gammas. And then the weighted sum of the log probabilities at the node, where the weight is the gamma itself, summed over all time, is going to give me the overall divergence. Yeah?
Why can't we calculate beta direct? We calculate beta add and then we calculate beta direct.
You could, but then, it's a little more, you'd end up with 2 summation terms. So this is just convenience, that's it.
And gamma is normalized beta.
Normalized alpha beta, right? You're normalizing down the column. This is the posterior probability of aligning the rth symbol to the tth input. That's it, okay? And so once we do this, we have my divergence, and we can compute the derivative of the divergence for backprob. Had a fever all night.
Your microphone battery is low. Do you have a backup battery?
I do. Wait. Yeah. Sorry. I didn't mean to. Okay, this was an easy one, guys. Anybody want to answer the first? Is the first statement true? Second one. Okay, easy. Thank you. Okay, so here's where we are, right? We have managed to compute the divergence. And the divergence is the average divergence or the expected divergence over all alignments. Now remember that was computed using this graph that was composed by pulling rows out of the probability table output by the network. In order to train the network, what we really want is the derivative of that divergence with respect to the output of the network. So now this means that there's a divergence that's been computed from this graph. I want the derivative of the divergence, for instance, with respect to all of these probabilities. Now, if any symbol doesn't occur in the upper graph, what is the derivative of the divergence with respect to the probability of that symbol? It's going to be 0 because it doesn't really occur in the graph, right? So you only end up with non-zero terms for the actual symbols that occur in the target symbol sequence, number 1. Number 2, we want to compute the derivative of this divergence with respect to all of these probabilities. We know that most of them are going to be 0. Some of them are not going to be 0. And for those in particular, we want to this is for at any given time. So if I choose my time, this outer summation goes away because you're focusing on just one time, right? So at any given time, you just have to compute, you have to go up the column and compute the derivative of this guy with respect to that symbol. So here's what that would be. These derivative terms must be computed from here. And so let's say I think of the probability assigned to the symbol E at time 3, right? So if I'm considering the probability of the symbol E at time 3, I just need to consider t equals 3. The rest don't have to be considered. Furthermore, if you look at this summation, this summation includes E twice from the second row and the fourth row, right? And so I'm going to have to sum the derivative of the product of gamma and log y at the second row and the fourth row with respect to y. Is that making sense? Right, and so now that reduces to computing this term. So here, for E, I'd be summing the derivative of this term at those two nodes. Now, what is the derivative of gamma log y with respect to y? Anyone? 1 by y? Is that it? So it's actually going to be, what's the derivative of this term here?
Gamma by
It's going to be gamma over y times the derivative of gamma times log y, because gamma also depends on y, does it not? Okay, it turns out that this is very easy. Computing this guy is really ugly. And now, when you end up with a term that's very ugly to compute, how do you solve it? You come up with a reason to not do it, and then don't do it, so you just throw it away. And so you just say, I'm going to ignore the second term. I'm going to assume that this guy doesn't exist. And the mathematical justification for this is that this now gives me a maximum likelihood estimate. And now once you've justified it, you don't have to do it. And so the rest is easy. It's just gamma over y, right? And so the derivative of this divergence with respect to, so it's very satisfying. We went through a whole bunch of math, but at the end of the day, it's satisfying. What is the derivative of the divergence with respect to the output probability assigned to any symbol r at any time t? It's just this. It's -1 over the probability assigned. This is what we normally get in any case. There's an additional weighting term, which is just the sum of the gammas for all the nodes that invoke that symbol. If that symbol is not invoked, it's going to be 0. If there's only one symbol, it's going to be 1. If this, so it works out very nicely. And so once you can compute this guy, you're able to compute the derivative of the divergence with respect to the output of the network, entire output of the network at each time. And then this can be passed back to complete backprop. So here's what we'd have, right? You'd set up the network, typically a many-layered LSTM, initialize all the parameters of the network. Then in the first forward pass, you'd compute the output probability table. Then from this, for each training instance, you're going to pull out the appropriate rows from this table to construct the reduced table and the graph from it. And from the graph, you'd perform forward and backward algorithms to compute the alphas and betas. From the alphas and betas, you can actually compute the gammas. And then once you have the gammas, you actually have the, you can use those to compute the derivative of the divergence with respect to the output of the network at each time, which gives you the derivative of the divergence with respect to the output probability vector. And this can be propagated backwards to train the rest of the network. Now, if all of this was very confusing, you're going to do this in your homework, so it will make less sense. Okay. So here's what we find. This is what we call the Connectionist temporal classification network. Sequence-to-sequence networks which irregularly output symbols can be decoded through a greedy algorithm. They require alignment of the output to the symbol sequence for training, and this alignment is generally not given. So training can be performed by iteratively estimating the alignment using Viterbi alignment and time synchronous training. Or it can be performed by optimizing the expected divergence over all possible alignments, in which case the posterior probabilities for the expectation can be computed using the forward-backward algorithm. So far, so good, right? But in all of this, I've ignored one key problem, so consider this situation where the output symbols are characters. We said we can just repeat symbols when we decode, right? So let's say a decode came up with this RRR, 3 E's and 2 D's. Is this the word read or is this the word read? We don't know, right? There isn't enough information. It could have been either. So we need some way of distinguishing between repetitions of symbols. And so here's where a little bit of clever engineering comes in. So this was, again, the same thing that we mentioned in the last class, right? I can't distinguish between repetitions and a single instance. So we're going to introduce a new symbol. This new symbol is an invisible symbol, meaning it's there, but you don't see it. It can be output at any time. So here, for example, here's an alignment. RRR, this invisible symbol, which you typically represent using a blank, 3 blanks, 2 E's, 3 blanks, and 2 D's. Now, when I compress it, I get an R. I get the invisible symbol, but it's not seen, right? Then I get the E. Then there's the invisible symbol again, but it's not seen. And then I get a D, so it becomes a red, right? So here, for example, this is R, E, but then in between there's an invisible symbol. So then it separates the second E, and there's a D, right? So this is going to be R, R again, E, D again, and D again. So you see how the invisible symbol works. It's there, you just can't see it, right? So if that is the case, what would this compress to? Anyone? Mm-hmm. Triple R, double E, triple D, right? That's because, again, so this means that this has the nice habit of actually identifying or distinguishing repetitions from just an extended sequence. This is done by the invisible symbol. And so here's a poll. Okay, someone on Zoom, can you tell me if the first one is a valid expansion of Billy? Zoom?
No.
Okay. What about the second one?
No.
Zoom again. Is the second one valid? No, okay. Someone in this room, what about the third one?
No.
Is that valid?
No.
Is the third one not valid? Okay. Fourth one?
Valid.
Okay. So do you see how this works, right? So the invisible symbol has this nice property of actually making these repetitions unambiguous. And so, for instance, so the way you do it is actually introduce the symbol to your vocabulary. And then at each time, the network is outputting not only the probabilities of the seen symbols, but also the probability of this invisible symbol. And now let's say I just went through this guy and picked up the most likely symbols at each time. This is going to be 2 B's, 2 E's, F, E. This becomes B phi, right? But suppose the most likely symbols were these. Then what does this become? Over here. Anyone?
Double Y.
It's a? You were saying something?
B double Y.
It's going to be B. This is B. This is still B phi, right? Because this is B. The fact that there's an invisible symbol in the beginning didn't make any difference. So this is B. These guys are E. Then what followed was F, and this was an E, right? What about this one here? What is this? That's a double F because there's an invisible guy between the 2 F's. And so this sort of makes things very convenient. Now, how does this modify our training? Remember that, okay, 2 things. You can actually get an invisible symbol at the beginning of the alignment. You can similarly also get one at the end of the alignment. This is valid, right? The other issue is that when somebody writes down, when you get training data, does anybody actually mark the invisible symbols? They are not there. So you have to somehow learn the model for the invisible symbols, even though they are not actually tagged in the data. And so the way you do it is in how you compose the graph, right? So let's say I had this graph for this word eddy, E-D-D-Y, right? So in this case, if I'd done it the way we'd done it before, this was the graph we got, but then this has a problem. It's ambiguous. I don't know whether it's two Ds or a single D, right? And so here's what we do. We introduce blanks, these some invisible symbols. Now consider the word beefy. Here, I can have B. B can immediately be followed by E, or it can be followed by an invisible symbol and then an E, right? Similarly, E can be followed immediately by F, or by an invisible symbol followed by an F. Same thing. F can be followed by E, or an invisible symbol followed by E. And then you can have optional invisible symbols at the beginning and the end. On the other hand, if I have eddy, I cannot have, D cannot immediately be followed by a D again. You must go through the invisible symbol. Otherwise, you're going to collapse it and it becomes ambiguous whether you're saying EDY or EDDY, right? So that's how we use the symbol. When I represent the actual sequence, I'm going to have the optional invisible symbols when the symbols on either side are different. And if the symbols on either side are the same, the blank will not be optional again anymore. And so going back to our graph, here's how I'm actually going to be composing it. Earlier, this was the sequence for which I pulled out the rows from the table, right? The symbol on the left. I'm going to modify that. Now it's going to look like this. I have my eddy, but then observe what I've drawn on the vertical column. I've actually drawn the graph that represents the symbol sequence EDDY, right? With all the optional invisible symbols, the blanks marked in. So you can have an initial blank. You have the E. E can either be followed by a blank or can directly be followed by a D. D must be followed by a blank because you cannot skip the blank, otherwise the two Ds would get compressed. The second D can optionally be followed by a blank, or you can directly go to E. And then after E, you can have an optional blank. So when I compose and so the probability rows that I pull up, these rows correspond to all of these symbols over here. And then when I draw my graph, I'm going to draw an edge between any two nodes that represent, such that the edge represents a valid component of an alignment, which means that I'm always going to have, for example, an edge going from D to blank, so the downward blank. But then D can also directly skip to E, right? So I also have an edge going directly from D to E. But out here, D must be followed by a blank, so I have an edge going from D to E, but there's no skip arrow over here, so I don't actually have an arrow going 2 steps down. Yeah. Is this picture making sense? So this is basically just unrolling the graph I drew to the left over the input. Okay. Once I draw this graph, the rest of the problem becomes straightforward. How so? First, the first and last columns are also allowed to end at initial and final blanks. Okay? And so you have 2 possible start points, the blank or the initial E. But then if you go through this graph, every path through this graph represents a valid alignment of eddy to the input with blanks considered, right? And there's no path which is an alignment of eddy to the input that's not in this graph. So this is complete. And now once I compose this graph, again, the node probabilities are just drawn from the probability table that the network outputs. Is this picture making sense to all of you guys? Right? I'm still left with the same problem. I want to compute the average divergence over all of the alignments, right? How would I compute the average divergence? I'm going to sum over time. I'm going to sum over the columns, and I'm going to take the expected negative log likelihood over the column. And so in order to compute the expected log likelihood, I need expectation. I need the posterior probability of every node in the graph within the column, and that's going to be computed using the forward-backward algorithm. So the distinctions here are that skips are permitted across a blank, but only if there's if the symbols on either side are different, otherwise they're not. Like that's the only extra consideration in composing this graph. Yes?
On Zoom, someone is asking why we need the initial and final blanks.
So it's an invisible symbol. So by the rules of the game, if it's not there, you're allowed to have invisible things at the beginning and the end. That's all. It's not mandatory, but logically it makes sense that if I have an invisible symbol, it could occur anywhere, right? And so long as the invisible symbol, the presence of the invisible symbol doesn't violate the correctness of your alignment, you're still good. That's all. Okay. And so now, here's how I do my forward algorithm. Now I can have non-zero alphas, but 2 nodes in the first column, right? So alpha 0, 0 is the y0 blank. Alpha 0, 1 is the probability assigned to the first symbol. And then the alphas are going to be zeros for all the subsequent entries in the graph. Then I can take a step forward, and the rule I'm going to be using is very simple. At each node, I'm summing the alphas of all of the parents and then multiplying it by the node probability. Except that some nodes have 2 parents and some nodes have 3 parents. Now, what is the rule for determining whether a node has 2 parents or whether it has 3 parents? Every node definitely has 2 parents. T minus 1 R and T minus 1 R minus 1 are both parents. And if this symbol is not the same as this symbol, then R minus 2 is also a parent. Otherwise, it's not. This makes sense? This considers everything, right? The fact that you can't skip symbols, that the fact you can only skip a blank if the symbols on either side are different, and so on. And so I can just use this rule and compute my alphas going forward all the way to the end of the graph. Similarly, I can now compute my betas. The beta hats are going to be non-zero only for the bottom 2 nodes of the graph. For the rest of them, the betas are going to be 0. And then these are just going to be, the probability of blank and probability of E in this case, right? Those are the node probabilities. Then I can work my way backward using the simple rule. At each node, I'm going to be summing up the probability of the betas for all the children of the node, and then multiplying that term by the node probability. And I can keep working my way backward. If I want to specifically see how this works for this graph, every node has at least 2 children. So, and if the symbol 2 symbols down is different, then that thing is also a child, otherwise it's not. So applying the rules, every node has T plus 1 and T plus 1 R plus 1 as children. And if the 2 symbols are different, T plus 1 R plus 2 is also a child. So once you sum up the beta hats, you multiply it by the node probability, you get beta hats going back. What you really need is beta, so you have to divide by the node probability, and which is this term over here. And once you have the alphas and betas, you can compute gammas just as before. Any questions? Yeah.
If S are unequal, we are considering R plus 2 also, right? So that's the options blank, right?
No, the R plus 2 is for this guy. So here, D is followed by E. Yeah, in this case, it's optional blank, right? D can definitely be followed by a blank. And you can skip the blank if these 2 symbols are different. That's the R plus 2. Right, you're right. Okay. Yeah.
Question. On the previous page, you first times the beta hat by YTSR, and then you divided it by the YTSR. So can you just omit?
So here is the thing, right? If I want to, you can absolutely do this. All that happens is, if I wanted to write it without that, and directly work this in terms of beta R, then you're going to end up with beta TR equals sum over children. L belongs to children. beta TL, actually no, t plus 1L times y t plus 1L, because you have to account for the node probability at the next instant. So I can either multiply by y once and divide later, or multiply every child by the node, right? That's all. This is just simplification. I'm using the same algorithm as the forward algorithm in this case. I can just flip the entire graph, use my forward code, and things work, right? So posterior and derivatives are computed exactly as before, but using the extended graph with blanks. So if you want the overall training procedure, here's what it's going to look like. You're given an input and output sequences without alignment. We want to train our models. You set up the network, typically a multi-layered LSTM. You initialize all the parameters, but now we're going to introduce the invisible symbol, the blank, in your vocabulary. And so the parameters for this are going to be initialized as well, right? Now observe that although the blank was never explicitly mentioned in your training data, it got implicitly included by the manner in which you compose the graph. So you end up learning probabilities for the blank as well. And then once you do this, for each training instance, you perform the forward pass, you compute probabilities for all symbols in your vocabulary, including the blank. Then you compose the graph. Now note that the graph actually includes blanks. And then you can perform a forward pass through the graph and compute the alphas for all the nodes in the graph. Do the backward pass, compute the betas for all the nodes in the graph. And then from the alphas and betas, you can compute the gammas just by multiplying alphas and betas and then normalizing down the column. And once you've done that, you can compute the derivatives of the divergence with respect to the y's at each time. I mean, all the same rules apply, just the same as before. And now you have the derivative of the divergence with respect to the set of probabilities computed by the network for all the symbols at each time. So basically, the gradient of the divergence with respect to the output of the network at each time. This can be propagated backwards to train the model. Yeah.
Wouldn't it be more efficient if we only introduce blanks where necessary? Because like now the size of the graph is much bigger than it was originally.
So again, once you begin doing that, things get a little more complicated. How do you define those blanks? They become very specialized. Whereas if I just say, I have an invisible symbol, that's more generic, right? Occam's principle, you want to go with the simplest solution. You just say, I have this extra symbol, it's invisible. That accounts for everything. You can't say, I have an invisible symbol that only occurs between repetitions. Then it becomes a lot more, ugly to justify it. Yeah.
Does the graph for the modified forward differ from the modified backward? Because we have like the notation of whole like sort of top for.
The graph is exactly the same. Nothing changed, right?
No, for one slide down. That forward pass.
This is the graph we'd use for the forward pass. We'd use the same thing for the backward too.
Oh, okay. Yeah, there was like one slide, like 2 slides back, where you have right here. No, forward. Yeah, right there.
This is just the output table.
Oh, okay.
Right. This is what the network is generating. You use this to compute the graph, compose the graph, right? So easy. And so this overall framework that we just saw is referred to as Connectionist temporal classification, applies to models that output order aligned but time asynchronous symbol sequences, okay? So now, can you turn your phone upside down? Please. Again, the next time I see you guys with a phone, I'll ask you to go outside, finish your job, and come back. Anyway, there's one final thing we have to consider. When we were speaking of performing inference, we said I can just, you're just given data, you're given the model, you're asked to determine what the output is. I said the simple way of doing it is to just pick the most likely symbol at each time. Yeah.
Someone on Zoom is asking, do we use the same, that is the invisible symbols, when working with other modalities like visual modalities?
The notion of an invisible symbol is generic. So if you were doing handwriting recognition, you'd have the same thing, right? That's the idea of an invisible symbol. That's a very creative, invention that they came up with and solves many problems. And again, you don't want to make specific, specialized things for special settings. You just add something that you say, I can't see. It's very pretty, right? So when we spoke of inference, we said we can just pick the most likely symbol at each time. And we said picking the most likely symbol at each time causes, ambiguities with respect to repetitions. But once we introduce the blank symbol, that problem goes away, right? But before that, right, let's consider something else. The greedy decode is just picking one possible time-aligned output. Now, I can have many different time-aligned outputs. So let's say, and let me pick up these 3 examples, right? I have a model which assigns the probability of 0.7 for RR blank EED, right? It assigns the probability of 0.68 for RR double blank double D, and ED, and 0.69 for RR triple ED. And then for TED, one alignment has a probability of 0.71, but the others have 0.3 and 0.29. If you pick the most likely output, which one would the greedy decode pick up? It's going to pick up TED. It's the most probable sequence, right? But then if you look across all alignments, which is more reasonable? Red, right? It says even for minor jitters, I have high probability. So what we really want to find is the symbol sequence that has the highest overall probability across all alignments. Now, as it turns out, greedy decoding still does a very good job for these CTC models, and that has to do with the manner in which they behave. It turns out that for the non-blank symbols, the probabilities typically just peak at transitions when you're going from one symbol to the other. And so, when you're staying within a symbol, it tends to just assign the highest probability to the blank symbol. So a greedy decode does a pretty darn good job. But our point is, we want to pick the most likely order aligned sequence across all alignments, not just the symbol sequence that had the most likely single alignment. And so how can we do that? We want to find the compressed symbol sequence that has the highest probability given the input, which means I want to sum the total probabilities of all alignments of the symbol sequence to the input, and then pick the symbol sequence for which this total probability was highest, right? And what was the total probability of all alignments? Remember, when I aligned a symbol sequence to an input, the alpha down here is the total probability of all alignments of the symbol sequence to the input, right? And so what I want to do is to compute for every possible symbol sequence, output sequence in the world. I want to compute the alpha at the bottom right, and then pick the symbol sequence for which this alpha was highest. But is that feasible? I'm going to have to compute the alpha for every possible symbol sequence. How many of those are there? Come on, guys.
There was 6.
6? I'm giving you just, I say here is this input with 10 of 10 vectors. I have my vocabulary of 100 symbols. How many possible symbol sequences can I consider? Order of 100 raised to 6, right? Or 100, it's n raised to t. It's exponential, it's going to be huge. And so you can't possibly consider every possible symbol sequence, compute its alpha, and pick the symbol sequence for which this alpha was highest. That's infeasible and an impossibility. That makes sense? Mm-hmm. Right. So, I mean, if that, let's say, just as an illustration, if my symbols are just A, B, C, and there's an additional blank as well, right? But let's ignore blank for now. And then if I have an input which is 9 symbols long, what are all the symbol sequences I can have? I can have just A for the entire input. I can have AB. I can have ABC. I can have AA, BC. I can have BA. How many of these will I get? So I can have 3 plus 1, where there's an invisible symbol over here. 4 raised to 9. Those are the various number of combinations I would have to consider, right? Do you really want to explicitly compute the alphas for all of these guys? You don't want to do that. So is there an efficient way of doing this? Yes.
Would it be very sharply peaked in terms of the probability?
How would you identify the one for which it's sharply peaked? Right? You're going to have to, in principle, you're going to have to evaluate all of these guys. And so again, there's an engineering solution to this. You want to find the most likely asynchronous symbol sequence. So here's a poll first, and then I'll go through this fairly quickly. Yeah.
Is that going to be 4 to the power 9 or 3 to the power 10?
4 to the power 10. Right? You can have blanks separating things. It's upper bounded by 4 raised to 10.
Okay.
It's going to be lesser than that, but still a very large number. Okay, let's rush through this. What's the answer to the first one? True or false? Can everybody say true together? True. Thank you. Second one? Also, right? We want to find, the objective of decoding is to find the compressed sequence that has the highest probability. This is the same as finding the compressed sequence with the highest alpha for aligning the final symbol on the sequence to the final input, and this is expensive. So, explicit computation of this is going to require evaluation of an exponential number of symbol sequences. So what we will do is organize all possible symbol sequences as a semi-tree. I'm going to run over a couple of minutes. Bear with me, guys, right? Let's say, I'm giving you a toy example. Let's say my vocabulary has only 2 symbols, S1 and S2. Now, as I showed you, I have to implicitly also include the invisible symbol, the blank. So let me represent all possible symbol sequences as a tree. I can either have a blank in the first position or S1 or S2. Then S1 could be followed by S2. If S1 must be followed by S1, S1 must be followed by blank and then must be followed by S2. But if S1 is followed by blank and then by S2, that's also an S1, S2, right? Similarly, at the bottom, S2 can be followed by S1, or S2 can go through a blank and be followed by S2. But then I can also have blank followed by S1, right? So if I look at all possible symbol sequences, they are represented by this graph. It's not strictly a tree. I'm calling it a semi-tree because you have certain, convergences, right? So now, here's what I can do. I can draw that semi-tree up here in this vertical axis. This is time. And this is just the same kind of graph that I used to perform the forward-backward algorithm, right? Now, here's the thing. Every node in this graph represents a unique symbol sequence. This node represents S2, S2, S2. This node represents S2, S2, S1. This node represents S2, S1, S2. You can see how every node represents a unique symbol sequence, right? Yeah.
This tree is only considering mandatory blanks. It's not considering optional blanks.
There is an optional blank. So, I can have S1, S2, S1, S2 blank S1, right? Everything is considered, right? Yeah.
How do you account for extra blanks you need to skip?
So this is just the compressed sequence. So here's what you got, right? When I unroll it, this is what it's going to look like. Every row represents a unique symbol sequence. And repetitions just mean you're walking down the row, right? And so on this graph now, if I have 4 inputs, I'm going to actually have to perform the forward algorithm all the way to the end, then pick the node for which the probability was highest and the corresponding symbol sequence is going to be my most likely symbol sequence, right? Now, what would the probability be with just, the problem be with just computing this directly left to right?
Blows up.
It's going to blow up. As the number of inputs increases, this graph becomes larger and larger. As computer scientists, how would you solve this?
Ignore things you don't want to see.
Anybody else? How would you solve this? So this is what we do. We do beam search, right? So again, the forward at the final time represents the full forward probability. Select the symbol sequence with the largest alpha at any time. But we can't compute this directly. It's going to blow up, right? And of course, if I want to compute the probability of any particular symbol sequences, I have to sum two alphas. Remember, both of these are valid outputs, right? So I have to compute the sum alpha RT and alpha R blank T. But that's besides the point. The point is I need to be able to compute the forward algorithm here, and that's very expensive, so we do something very simple. At the very first time, I can draw this graph. At the very first time, I can go up here. But then I can only retain the top 4 most likely nodes, for instance. Then I expand only those guys, and then retain only the top 4 most likely nodes, and keep doing this. So this is beam search. And so once you actually decide on a beam and you perform a beam search, the computation is going to be limited, finite, and you can run through your entire input. Now this is, not optimal, but it's pretty close to optimal. And then once you've run out of the input, you can actually pick the symbol sequence for which the alpha was highest. You have to consider 2 terms, S1 and S1 blank, both represent the same symbol sequence. You'd sum their probabilities to get the probability of S1. So you add, once you do that, you're going to pick the symbol sequence which is most likely, right? So I have some pseudocode in the slides. I'm going to skip those and check them up because it's going to appear in your homework. But here's the thing. CTC models are sequence-to-sequence networks which irregularly produce outputs. They can be trained by iteratively aligning the target output to the input in time-synchronous training, or optimizing the expected divergence over all possible alignments. Distinct repetitions of symbols can be disambiguated through the introduction of blanks, and decoding can be performed by greedy best path decoding or through beam search, right? And so there are multiple ways of dealing with the repetition problem. Blank is just only one. I'll skip that. And we'll go on. So that's the end of this. The most common applications are speech recognition and handwriting recognition, but there are also other problems where you can have order aligned but time asynchronous outputs. And anywhere you have something of this kind, you can use the CTC model. For instance, if you're periodically reading stuff off the stock market, this is what would apply, right? Or aperiodically reading stuff.
How do we decide on the most likely nodes in beam search?
Most likely?
Nodes?
The one that has the highest probability. That's it, right? The alpha is highest. Yeah.
How do we decide how many beams we're doing? You said.
The size of the beam is going to be heuristic, right? So the larger the beam, the more accurate you're likely to be, but the more the computation is going to take.
Okay.
It's a trade-off.
Can you do something like a beautiful beam sense, like while you decode
You can do that. Okay, thank you all. I will see you next week.